Hi YouTube, continuing Core 4 2008, question 6. Given two lines to show that they meet, to find the position vector in A, to show that they're perpendicular in B, and given the point A, to show that A lies on the first line in C, and the point B is the image of A after reflection in L2, to find the position vector of B in D. So given the two lines, considering an intersection, then minus 9 plus 2 lambda will be equal to 3 plus 3 mu, and lambda will be equal to 1 minus mu. So solving simultaneously gives values for mu and lambda. So the lines intersect, and substituting lambda equals 3 into L1 gives a point, and we can write down the position vector. So to show that they're perpendicular, the dot product of their direction vectors will be 0. They are perpendicular. So considering A lies on L1, then minus 9 plus 2 lambda will be 5 for A on L1, giving lambda equals 7. So using lambda equals 7 for the vector equation, A lies on L1. So for the position vector of B after reflection in the line L2, considering they're perpendicular to each other, then if the intersection is x, the ratio ax over xb equals 1 to 1 will be satisfied. And cross multiplying and simplifying gives b as 2x minus a. So using the intersection point for x from A and substituting gives the position vector of B required. The intersection point, they are perpendicular, and the coordinates B and the sketch here shows line L1 and L2 and the intersection X. Question 7, differential equation, partial fractions in A and the particular solution of the differential equation in B, giving the answer in the form x squared x equals gy. So for part A, partial fractions, considering the form a over 2 minus y plus b over 2 plus y, multiplying both sides by the lowest common denominator gives the identity here, and trying y equals minus 2 and the constant, we can write down the partial fractions. So for part B, the differential equation given, we see it's separable. So separating and considering the partial fractions from A, applying the partial fractions and integrating both sides gives our general solution. And given y equals 0, x equals pi over 3, substituting evaluates the constant as minus ln2, giving the general solution here. So considering the required form, using the laws of logs on our general solution and simplifying gives this expression, and simplifying to the form required. partial fractions in A, the general solution and the particular solution. Final question in this paper, question 8, trigonometry parameters. To find the value of t at the point P in A, we're given that the line L is a normal to the curve at P. Show that an equation for the normal in B, and to show that the area of the shaded region will be this integral in C, and then to evaluate in D. So for part A, for the value of t at P, given x equals 4 at P, and solving the parameter for x gives t equals pi over 3. So for the equation of the normal in B, differentiating for an expression for dy dx for parameters, and substituting t equals pi over 3 gives our gradient, and the normal gradient will be minus root 3. So then using the point given with the gradient simplifies to the proof required. So for the area of the shaded region at x equals 4, t is pi over 3, and considering 0, then solving 0 equals our x parameter gives t equals pi over 2, so limits pi over 2 and pi over 3. And considering the integral for parameters for area, applying to the integral y dx dt dt, it simplifies to here, and flipping gives the proof required. So evaluating this integral in D, considering the substitution u equals sin t, adjusting the limits and applying to the integral, gives 64u squared du, and integrating and evaluating gives the area required. Solving for t in A, our expression for the gradient of the normal, and the equation of the normal, the given integral for, and the substitution, and the integration, and the exact value, and the exact value direct. Thank you for watching. I'll start further Pure 1 in the next video.